Okay, so this is part 2 to the review for test 2. I just didn't want to do it in one long video. I am going to be giving you all of these finance/economics formulas, so keep that in mind. So the relative rate of change formula is the derivative function over the original, and we'll need that for number 20. So notice at number 20 you're given that the f of x is 72 and then x is 230. So if we want the relative rate of change, we need to find the derivative of the original. Notice that's not that interesting, right? The derivative, it's going to be f prime of x over f of x, right? So the derivative of 72 is just 0, and then of 72, notice this is 0, which means that the relative rate of change is, again, not that interesting in that problem. It's just 0. So what about in 21? It's a little more interesting in 21. So 404 minus 4x, where x is 38. So notice this is also asking for relative rate of change. So you're going to do the derivative over the original. The derivative of 404 minus 4x is just negative 4. And then the original is 404 minus 4x. Now notice, sometimes you'll have an equation for the derivative. In this case, we don't. Okay. So then you would just plug in 38. So you could simplify here as well. Okay, I think I did on this one. So what I did is say, hey, 4 goes into this once, 4 goes into this 101 times, 4 goes into this once. So I think I wrote negative 1 over 101 minus x here. But then you're going to plug in x equals 38. Notice there's nothing to plug in on the top, but on the bottom we'll have 101 minus 38. And so if you write a decimal, it's negative 0.016. Okay, so that's relative rate of change. Starting with 22, if we want percent rate of change, that is the same formula that we just used in the previous 2 problems, just times 100. In other words, move the decimal place twice so that you can talk about a percentage rather than just a decimal. So for f of x, for this one it's 476 plus 161x, and we want it when x is 2. So the percent rate of change is going to be, the derivative is 161. The original was 476 plus 161x, but then don't forget we need to times it by 100. So at x equals 2, we're just going to plug in 2. Everywhere there's an x. In this case, we only have one place there's an x, but for the one you get on the test, it might be more than that. And this will come out to be, not surprisingly, a percentage answer. Okay, so if we have a positive percent rate of change, it indicates that our values are going up. All right, let's look at 23. F of x equals 18,000 minus 4x squared, and x is 65. So again, it asked for percent rate of change. So you're going to find the derivative. This time it's an equation, not just a number, right? The derivative of negative 4x squared is negative 8x over the original function. And then again times 100. But if we want it at x equals 65, we just plug in a 65 everywhere there's an x. So we have one on the top and also the bottom. So punch that in your calculator. Notice this is an approximate, and we get negative 47.3%. Okay, that means the values are changing relatively by 47.3% in the negative direction. It means they're reducing. All right, so 24. On 24, you're supposed to find using the price-demand equation, you're supposed to determine whether it's elastic, inelastic, or unit elastic. I will give you the formulas. I probably am not going to tell you how to tell whether it's elastic, inelastic, or unit elastic. So plan to get the E of P formula, okay? So remember, E of P, the formula is negative P times F prime of P over F of P. But I don't necessarily plan to give you when it's which one. Okay, so for 24, notice we have X equals F of P, right? So on 24, I already gave you the equation in terms of P. If it's not in terms of P, you need to get it in terms of P. So let's figure out the E of P equation. So it's going to be negative P, right, that's the formula, times the derivative, right? The derivative is negative 60P. If you move the power out to the front, you get negative 60P. And then all of that over the original, which is 7,290 minus 30P squared. So if you clean this up just a little bit, and you can clean it up more, this would be 60P squared over 7,290 minus 30P squared. But in the end, all we're really trying to do is plug in the number at this point. So let's just plug it in here. Again, if you want to reduce that, you can. It's just not completely necessary for this one, since all I'm asking you for is kind of the final result. So if you plug this in, you get 200 over 143 if you use math fraction on your calculator. I'm going to zoom out. I keep forgetting that this is a lot bigger. I keep being off screen here, trying to zoom out. Okay, notice that this is larger than 1, okay, which means that it's elastic. Anything where your E of P is larger than 1, it means it's elastic. Okay, for 25, we have F of P equals 10,980 minus 7P minus 0.4P squared. And we're supposed to do this for P equals 90, for P equals 100, and finally for P equals 85. So in other words, find the elasticity equation and then plug in the different values. So that's what we'll do first. So E of P is going to be negative P times the derivative. So the derivative of this is going to be negative 7 minus 0.8 P, and then all over the original. The more simplified you make this, the easier it is to plug things in the end, okay? But honestly, you can leave it just like that if you want. But this comes out to be 7P plus 0.8P squared, and then over the bottom. So I think you can at least clean it up that much. But then you're just going to plug in the numbers. So plug in 90. I'm going to skip a little space. Plug in 100. And then finally plug in 85. Okay, plug it into that equation, right? So this one would be 7 times 90 plus 0.8 times 90 squared over 10,980 minus 7 times 90 minus 0.4 times 90 squared. So if you work this out, let's make sure, but you would want to make sure that you put parentheses around this on your calculator. So I'll go ahead and show what I'm doing here. So 7 times 90 plus 0.8 times 90 squared. That goes on top, divided by parentheses, 10,980 minus 7 times 90 minus 0.4 times 90 squared. Notice I get a 1, okay, which means this is unit elastic. That means they're going up by the same percentage. Okay, same thing here, you're going to plug in the same equation, right, with 100 plugged in. Try to get exact answers if you can, so use math fraction on your calculator. 435 over 314 is what you get. That is greater than 1, so it's elastic. Okay, anything bigger than 1, okay, whether it be a whole number or a decimal. And then lastly, 7 times 85 plus 0.8 times 85 squared over 10,980 minus 7 times 85 minus 0.4 times 85 squared. If you work that out, you get 1275 over 1499. Again, I just do math fraction on the calculator. It does it for me really nicely, which is less than 1, which means it's inelastic. Okay, a fast food restaurant can produce a burger for $1.55. We had a problem like this. Remember, it was a really short one. If the restaurant's daily sales are increasing at the rate of 400 hamburgers, or sorry, not 440 hamburgers per day, how fast is the daily cost for the hamburgers increasing? That is a real simple calculation. It's 155. This is the cost per burger. And so if you increase the burger sales by 40, you just multiply the two. So your costs are increasing by $62 a day if your burger output increases by 40 per day. Okay, so there's not really a whole lot to that one. All right, so 27, notice that they gave us that x plus 200p equals 1500. So this is one where it's not really written correctly. So the first thing you need to do is tell me what x equals. You need an equation involving p. So notice if we subtract that over, we'll have it, right? So 1500 minus 200p is the equation we'll use. So the elasticity equation, again, it's not on screen anymore, so I'll write it again. Negative p times f prime of p over f of p, okay? Just to remind you, I'll have all these formulas for you. You just need to know how to use them. So it's negative p times the derivative, which is negative 200, and then over the original, which is 1500 minus 200p. So in the end, you get 200p over 1500 minus 200p. Technically, you could cancel 100 out of everything. Don't cancel a p, though. You're not allowed to do that. So if you plug in, I think the problem mentions that currently the price of the burger is $2.50. So you're going to plug in 2.5 and see kind of how resistant or how open this is for demand to change. Okay, so if you plug in 2.5, which is the cost of the burger now, you are going to get, just trying to make sure I have the right numbers here. Sorry, I do. You're going to get 0.5, okay, which is less than 1, which means it is inelastic. So if it's inelastic, remember what that means, okay? Inelastic means it won't change, okay? So the demand won't change much. Okay, it doesn't mean it won't change, it means it won't change significantly. So if the demand won't change much, in other words, if our price increase won't cause people to not buy our burger, then a 10% price increase will increase our revenue. In other words, we're not going to have the problem of too many people saying, hey, I don't want your burger anymore. Okay, so we can go ahead and feel free to increase the price if we're looking at profit. So same kind of question for 28, a little different. So we have x plus 1300p equals 700. So x equals f of p, or 700 minus 1300p. So I moved the 1300p over so that I had the right kind of equation. So my elasticity equation is negative p times the derivative, which is negative 1300, over the original. So I get 1300p over 700 minus 1300p. Okay, notice in this problem it says what price will maximize the revenue. Okay, and so what I want to find is kind of when this is a unit elastic. Okay, so I'm going to set that equal to 1. So if you cross multiply here, in other words, think of this like 1 over 1, right? So in other words, these things are equal to each other. So I can say that 700 minus 1300p equals 1300p. So if we move things over, I get 700 equals 2600p. I'm trying to solve for price, right? So then last but not least, I need to divide by 2600, and then remember that I'm talking about money. So in the end, price is about 0.27. Okay, so sell the fries for about 27 cents. I know that's kind of an odd amount, okay, but that's what we get there. Okay, starting with 29, we are going to do all of the work. These are lengthy problems, okay? They require you to graph the equation kind of from start to finish. So let's see if we can kind of move through these kind of quickly. So I need you to look at the most recent lecture video if this is troublesome for you, okay? The one 12.4 is where you will find 29 through 31. So kind of keep that in mind. So I'm going to run through these kind of quickly. So the first thing is the domain. This is a polynomial, so it's just negative infinity to infinity. I'm going down my list. The next thing I'm supposed to find is x-intercepts. You do that by setting y equal to 0. I will give you something that can be factored on the test. So notice, even though this is an x to the 6th power equation, you can factor out what they have in common, right? They have an x to the 5th in common. So you're going to get 5x minus 7 equals 0. So if you solve, you get x equals 7/5 and x equals 0. I think on the key I wrote those as 2 separate points, so make sure you know how to do that, like 0, 0 and 7/5 comma 0. For the y-intercept, I'm just going to set x equal to 0. So f of 0 equals 5 times 0 to the 6th minus 7 times 0 to the 5th. So y equals 0, or again the point 0, 0. End behavior we haven't talked about since test 1, but end behavior is helpful here. So in other words, what is the limit as x approaches infinity of my function versus what is the limit as x approaches negative infinity of my function? So this is the far right, and this is the far left. Okay, so if you were to think of the biggest positive number you could, and you raised it to the 6th power, you're going to get another big positive number. So that's going to be infinity. But notice the same thing will happen here. If you raise to the 6th power a really large negative number, you're also going to get infinity. Okay, so what this means is that the graph goes up in both directions. Okay, because we go to infinity both to the right and the left. Okay, so now we're supposed to find, let's see, I'm going down my list. So we found domains, intercepts, end behavior, asymptotes. I'm at least going to mention this. Notice there are none, right, because it's a polynomial. So we'll at least make mention of that. Not all the graphs are going to have all the pieces, remember that. So first derivative, we're going to set equal to 0, so it's going to be 30 x to the 5th minus 35 x to the 4th equals 0. We are trying to find critical values, so notice these have 5 x to the 4th in common. So this would be 6x minus 7. So my critical values are 0 and x equals 7/6. These are critical numbers or critical values. So remember, those are the numbers that show up on your number line. So remember what this looks like, the sign chart. We put zeros here and here. So we want test points in all the sections. So the test points that I would probably pick are maybe -1 for the left, definitely 1 in between 0 and 7/6, and maybe 2 on the other side. Okay, and we're going to plug these into the derivative. So if you plug them in, just make sure you actually do that with your calculator. You're going to get a negative result here, a negative result here, and a positive result here. So what that means is that the graph is decreasing first. Now notice, this is not an undefined value, so it's actually going to decrease from -infinity all the way to 7/6. Notice I just kind of skipped over the 0 because it's just keep continuing to decrease. And it's increasing from 7/6 to infinity. Notice we have a change here, right? We were reducing and then we changed to increasing, so that means there's a min here. Okay, there's no maxes because there's no pluses to minuses. So then I just need to find f of 7/6. So plug that in. You get 5 times, definitely use your calculator, 7/6 to the 6th power minus 7 times 7/6 to the 5th power. So this comes out to be about -2.52. So the local min, not the local, but the relative min, some books call it a local min, is going to be at approximately 7/6, -2.52. The second derivative is going to be 150 x to the 4th minus 140 x cubed, and we want to set that equal to 0. So notice we could pull out a 10x cubed. If we did, we'd have 15x minus 14 equals 0. So here I get x equals 0 and x equals 14/15. That's just right under 1, by the way. So those are the numbers that show up on my number line. Notice, who cares that they're fractions, right? We can do them the same way. So on your sign chart, I get a 0 here and here, but this time it's the second derivative. So I'm just trying to figure out where my signs will be. So I'm going to pick some test points. I would probably pick -1 in between or to the left. Okay, I'm going to have to pick a fraction in between 0 and 14/15 because that's not even quite 1. And then to the left I can go ahead and pick 1. So remember what we're doing with this. We're plugging this into the second derivative. So if you plug them in, you get this pattern. You get a positive if you plug in -1, a negative in between, and a positive. So that means we are concave upward from -infinity to 0, and also from 14/15 to infinity. And we are concave downward from 0 to 14/15. Notice we have sign changes here, so we have inflection points at both spots. Inflection point here and here. So f of 0, if you look at that original function, that's just going to be 0. But f of 14/15, I'll go ahead and show that plugged in. 5 times 14/15 to the 6th power minus 7 times 14/15 to the 5th power. Okay, that is going to be about -1.65. Okay, so that means the inflection points, I'm running out of room here, the inflection points are 0, 0, and approximately 14/15, -1.65. That's a decimal point there. If you look on your key, you can get a pretty detailed graph. Just make sure you can go from the information you're given and come up with a decent graph. $30. All right, so notice we skip over 1, right? 1 is not allowed. I guess I need to write the right equation. 4 is not allowed. Sorry about that. So our domain is going to be -infinity to 4 and 4 to infinity. Our x-intercept, if we set y equal to 0, we're going to get 0 equals x plus 4 over x minus 4. Remember, in fractions, you just set the top equal to 0 when you want the whole thing to be 0. So my x-intercept's -4. My y-intercept, if I set x equal to 0, I will get f of 0 equals 0 plus 4 over 0 minus 4. So I get y equals -1. End behavior, this is all the way back again to Unit 1. End behavior is what's the limit as x approaches infinity of x plus 4 over x minus 4, but also what's the limit as x approaches -infinity of x plus 4 over x minus 4. But remember, the methods for doing these are the same. You put everything over the highest power of x, right, on the bottom. So you're going to get 1 there. I am shortcutting that, okay, so you need to go back and look at Unit 1 for that. Asymptotes, we set the denominator equal to 0. So I get x equals 4. The horizontal asymptote is the work that I did here. Okay, so I shortcutted it, but remember we put all the things over the highest power of the denominator. But you end up getting whatever you got for the end behavior, since the asymptote, if there is one, is the same thing as the end behavior. All right, now let's find the derivative. So bottom times derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So simplify that out, but if you distributive property, you're going to get -8 over x minus 4 squared. So you're going to try to set that equal to 0, but it can't be 0. We're trying to find out where the critical values are, okay? But also remember, critical values also include values that are off limits. Okay, notice x can't be 4 at all. So when you go to draw your number line, instead of there being a 0 here, remember we write a not defined. Okay, so I'm going to pick test points of probably 0 to the left, maybe 5 to the right. So in both cases, I'm going to get negatives. So that means my graph is decreasing from negative infinity to 4 and 4 to infinity. It's important that I skip over 4 because it's undefined there. Okay. Notice there's no relative extrema, both because I don't change signs, but also because I don't have, I don't even have a point at 4. 4 is not defined. So now let's talk about the second derivative. Okay, first I'm going to rewrite the first derivative. I can rewrite it as this. Okay, I rewrote that fraction as this. I did that because it's a lot easier to take the second derivative when I have it written like that. So power out to the front, reduce the power by 1 times the derivative of the inside. Rather than doing quotient rule again, I can do it this way. So I end up getting 16 over x minus 4 parentheses cubed. Try to set that equal to 0, but the numerator is not ever 0. So just like the last one, we also need to make note that x can't be 4. So we have to have another number line even though the numbers are the same, and that's because we're not checking the first derivative now. Now we're checking the second derivative. Okay, so these are different, in other words. So if we use the same test points though, x equals 0 and x equals 5, you're going to get a different pattern. You're going to get a minus here and a plus here. So that means we are concave downward from negative infinity to 4, and we're concave upward from 4 to infinity. There are no inflection points, even though we have a sign change. That's because, again, 4 is undefined. We can't have an inflection point if we don't even have a point there to begin with. So then again, just see the graph, okay? Notice you would graph all the information you have, and then you would pick some test points, okay? Or some additional points if needed, but you would get what's on the key. And then last but not least for these, notice these are really long problems, right? So I wouldn't expect any more than maybe 1 or 2 of these full-blown problems on the test. Okay, I'd be more likely to ask you things where I just ask you for portions of the problem rather than the whole problem itself. All right, so for the domain, remember we don't want the denominator to be 0. So we have x minus 6, x plus 6. So notice x can't be 6 or negative 6. So the domain is going to kick out those 2 values that aren't allowed. You can use a number line if you want and X out the ones that you're trying to kick out, but the domain is everything except negative 6 and 6. For the x-intercept, remember you just set the top equal to 0. So notice you're just going to get x equals 0. For the y-intercept, you set x equal to 0. So f of 0 is going to be 7 times 0 over 0 squared minus 36, which is just 0. Okay, end behavior is going to be very similar to the horizontal asymptote. So in behavior, we're going to do the limit as x approaches infinity of 7x over x squared minus 36. If you put everything over the highest power on the bottom, you will get 0 here. So that means when you get to the vertical asymptote, I'm going to do the horizontal one first. Your horizontal asymptote is just what you got here. Okay, end behavior and horizontal asymptote are very much intertwined. By the way, we already solved for the vertical asymptote too. It's wherever the off limits values for the domain were. We just set the denominator equal to 0. So now we're going to do quotient rule, bottom times derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So do distributive property, combine terms, and you should get negative 7x squared minus 252 over the bottom squared. Okay, you're supposed to be setting this equal to 0. So you're going to set negative 7x squared minus 252 equal to 0 and try to see if that will work. Okay, I'll just tell you that it's not going to. Okay, if we move the 250 over and we divide by negative 7, okay, so 252 divided by 7 is going to be x squared plus 36 equals 0. Okay, and this is imaginary solutions. In other words, if you try to move the 36 over, you're going to get something that doesn't work, right? So we're going to ignore this. In other words, there are no values that make the top 0 that are real numbers, okay? But we still have that x can't be negative 6 and x can't be 6. So even though we didn't have a value that made the derivative 0, we still have critical numbers. And those still need to show up on the number line. What shows up on the number line is anything that makes the derivative 0 and or anything where we're not allowed to be. Okay, so I'm just going to pick some test points. We've done this twice already in this review, so I'm going to kind of try to fast track this. So if you remember that these are not defined, and if you pick test points, so I would probably pick negative 7, 0, and 7 maybe, you're going to get negatives all across the board here, which tells us that the graph is always decreasing, but we will need to skip over those same unallowed x values. In other words, the way the number line is split up, we would include that in our answer here. That means there are no relative extrema because we have no sign change, but also because we don't have any values that are even defined marked on our number line. Second derivative. So I'll just be honest, I'm not going to be this mean to you on the test, but it's good practice of quotient rule. So bottom times derivative of the top minus the top times the derivative of the bottom. We have to use chain rule here. So 2 times x squared minus 36, but then times the derivative of the inside. That's supposed to be a 2x. So all over the bottom squared. So it's already squared, so when we square it, it becomes to the 4th power. Okay, so you're going to FOIL here. You're going to distributive property here. Okay, you're going to end up with 14x times x squared plus 108 all over x squared minus 36 cubed. I'm not spending a whole lot of time on this because frankly I'm again not going to be this mean to you, so if you can follow along, the algebra is what I skipped there, but I promise that's what you get. Okay, so if you set this equal to 0, notice that would mean we would set the top equal to 0. So we're not going to get anything here for the same reason we didn't above. We're going to get imaginary solutions, but if we plug 0 in here, we do get x equals 0. So this is kind of an interesting one, at least when we put it on the number line. Notice we still have negative 6 and 6 that are not defined. They stay undefined through the whole problem. So if I pick test points, I would need to pick 4 of them, 1 here, 1 here. So maybe negative 7, maybe negative 1, maybe 1, and maybe 7. You're going to get this pattern. So that means it is concave downward from negative infinity to negative 6, and also from 0 to 6. And it is concave upward from negative 6 to 0, and 6 to infinity. It also means that since we have sign changes here and here, normally speaking that would be inflection points, right? But we are not defined at these points. So these can't be inflection points, right? But 0 can be. Notice 0 is defined. So this is the only one that actually is an inflection point. So if you do f of 0, so plug 0 into the original, you're going to get 0. So 0, 0 is the inflection point, the only one. So if you combine all of that together, you'll get what's on your key, your solutions. Okay, the graph will end up looking like that. Remember, choose additional points if necessary. So again, these problems are really time consuming. So what I might do on the test is give you problems where you just find pieces of this. Or I might give you a problem where I've told you all the components to the graph and you have to combine them together and kind of choose additional points as needed and all that good stuff. Okay, so make sure you really know how to graph by hand. And you can see the notes from 12.4 if you are curious about any more of that. And then last but not least, we need to do the last one. Okay, I think increasing and decreasing are pretty self-explanatory. Okay, if you look at this graph, so let me kind of project it here. It is increasing until we reach, so I'm going to abbreviate here. It is increasing, remember we only use x values, until you reach an x value of -2. And then we start decreasing for a bit. Okay, notice it's decreasing from -2 all the way to x equals 2, and then it starts increasing again. Okay, notice there is a relative max. There's a peak, right? And the peak is present at -2, 3. And then there's a relative min. It looks like it is at -2, 1. Sorry, 2, -1. So I think most of us are most comfortable with the increasing, decreasing, max and min. But make sure that you can also do the concavity. If you look in week 7, I did a follow-up activity where we broke down some graphs with concavity. You might want to look back at that. But notice where it's making the change, okay, is actually right here. Okay, it's right in the middle. And so notice the curve is opening downward first from -infinity to 0. So this is concave down. And then from 0 to infinity it starts turning, right? Concave up. And then any point where we changed concavity is called an inflection point, and that is at the point 0, 1. Okay, so make sure, notice that the inflection point is not the same as the max and the min. Okay, so you need to kind of get that straight. Most of us are more comfortable with max and min than we are with inflection point. All right, so remember, the test will not be 32 questions. Okay, the review is intended to be a little more challenging than the test will be. In other words, if you can follow along and do the review, you should have no problem doing the questions on the test. Okay, so make sure you can work kind of quickly and efficiently, that you don't have to sit and think about a problem for too long. Okay, so just study as hard as you can and definitely email me if you have any questions.